until we get to some of the leading edge kind of questions in training machine learning models. And the aim of the talk is, more than anything else, to build a framework of understanding so that when you hear words like an Adam optimizer or a sort of an HE initialization process, there's a level at which you kind of know where to fit this within your understanding of neural networks or scikit-learn or otherwise. And kind of the aim of this, ideally, you should be able to define what we mean by an ML model rather than something else, what the general pitfalls in training them are, and which resources should you go to in the future. So the first sort of thing, and this is one of these slides that I would sort of wish I had been given earlier in my career in terms of what the various sort of resources and way that things are structured are when you're trying to understand the Python stack for machine learning. So at the 0th layer, you've got NumPy, or numerical Python, which I hope we've all opened up and used at some point. But there are some advanced stuff that people tend not to be aware of because either they learned it a while back or it's not there in books that were written in 2012. For example, I would always point out this @ operator, which is much better than the ... kind of thing for multiplying vectors and matrices. There's some rather impressive slicing functionality like the ellipses and num for slices that's rather nice. And again, if you don't know what a ufunc is, it's one of those things that I found occasionally quite useful within advanced NumPy. The book that I would recommend for this still is probably Python for Data Analysis, which is written by the guy that invented pandas, but also has some good resources on array-based programming and NumPy and advanced NumPy. At the next layer, building on NumPy, you have SciPy and pandas. SciPy extends basically numerical algorithms like optimization and things like that, the kind of things that NumPy views not fundamental enough to implement itself, and pandas is the thing that gives Python an Excel-like functionality. So if any of your colleagues at undergraduate went off into management consultancy and are paid enormous amounts of money to basically be very good with Excel, pandas is one way of getting access to that, plus a lot more. And I would generally say that pandas is often a data scientist's weakest point in terms of actually a good use and a confident use of pandas is something that people really, I find when I'm looking at sort of employing data scientists or postdocs or things like that, pandas is where they're missing stuff. So if you're looking to fill in gaps, looking into that is a good idea. And again, Python for Data Analysis, written by the guy that wrote pandas, is a good way to do it. Above that is scikit-learn, which can get a lot of bad press because it's generally a lot of very bad machine learning gets done by sort of downloading code from Stack Exchange and running it without thinking about it. But in fact, scikit-learn is a very consistent and powerful API and implements a lot of things that you often end up implementing yourself by hand, like normalization procedures and transformations and things like that. So again, confidence with scikit-learn, whilst less important than confidence with pandas, is actually quite good. There's a few sort of things, particularly these three words, knowing what estimators, transformers, and predictors do is quite a good thing to know about. And with a few key concepts, it's a very consistent and versatile machine learning framework, and actually a pretty good implementation of a lot of the standard things you might throw at a problem. And then above that, you have the big neural network guys and girls, which are the Keras and TensorFlow and PyTorch. And these are for deep learning that will come on to the second portion of the workshop. And basically, if you're familiar with the upper layers, these have become much easier to use. And then throughout all of that, you've got Matplotlib for plotting, which again is one of those things that is something that one must be good with. And whilst there are other things that extend it, like Plotly or Seaborn or things like that, I would always recommend Matplotlib at its basic for understanding that, because whilst others will extend it, they will usually reduce its flexibility. These three books I would recommend, particularly the middle one by Gell, which has been an inspiration for a lot of this talk, actually, or a lot of this workshop. So I would recommend the middle one as a very good thing that covers all of this up to the content of this talk. Okay, so anybody want to have a stab at defining what machine learning is?
It's inferring patterns in data using patterns from data, basically, using a computer.
Inferring patterns from data using a computer. Anything else? It's not bad. What separates machine learning from normal programming, for example? Because normal programming is sort of about patterns from stuff. Yeah?
It's less programmer/human interactive.
Less programmer/human interactive. That's not bad too. Yes. So I would always say this is the kind of the graph that will tend to show up at this point, where you have the usual scientific method / computer programming, which takes in models and data and produces predictions from those. Whereas machine learning is something that takes in data and predictions or inputs and outputs and produces models. Another way of thinking about it is it's something which a computer program which can program itself to perform a task. That's another way to think about it, i.e. it learns because it has some level of deep flexibility that is not human controlled. And this is good for any problem where you have lots of tuning or rules. Your classic example being a spam filter, which I mentioned as an example of machine learning there. You could, in principle, program something that you check to see what are the standard spam words that you might be seeing in an email, and you might sort of have a big list of them and have a sort of another program that has some kind of Bayesian model that says, oh, I reckon these words would increase the probability this is spam with some threshold that then cuts it out. But of course, spammers will then immediately change those keywords which they would use. So a machine learning program can learn those unknown parameters as it goes. It's good at solving, machine learning is also good for problems with no traditional solution, and where we can't solve it with traditional programs. Neural networks being the classic example, it's very difficult to imagine how the state of the art in Handley, which if you haven't seen what Handley can do, I would recommend Googling that. It's quite impressive where basically you type in, somebody types in free text like Darth Vader on a punt in Cambridge, and it produces an amazing picture of Darth Vader on a punt in Cambridge. It'd be very difficult to imagine how anybody could ever program that from first principles, even in the limit of an infinite number of computer scientists working for an infinite amount of time. It's very difficult to understand how a human could produce that. And it's also particularly good in fluctuating environments or adversarial ones, which makes it very useful against spamming or defense or cryptography and things like that. And on the other end of things, it's also very good for gaining insight about complex data immediately, like all these kind of visualization tools is one of the things where it's useful for. And again, that's sort of, just for example, lists some traditional programs and machine learning ones, where you have spam filters, Netflix suggestions, speech recognition, and Handley being good examples of these. So, when machine learning, there's generally a whole sequence of things, and we're really going to focus on 5 and 6, and in reality, the second half of 5 and 6, because selecting is its own art in itself, and we're really focusing on training and tuning machine learning models in this workshop. But just for completeness, when you're problem framing, that's when you talk about the big picture and you ask your employer or your PI or something else, what is the main problem that we're trying to solve here with machine learning, and you select what the targets are and look for any assumptions and biases that might be going into it from that point. You then acquire the data, and the dirty secret of this is that this is really the main bit of the game here. The reason why Facebook and Google are so fantastically good at doing some very impressive things is not because they've got the cutting edge of machine learning they do, but it's because they have all of the data. There's kind of this data resource that is much, much larger. And this is the idea where you have this thing that comes from a paper that's called The Unreasonable Effectiveness of Data in Machine Learning, which basically shows that your accuracy goes up with the number of the amount of data, pretty much independent of whether you throw the simplest memory-based task at it versus some sort of complicated neural network or other procedure. So in general, the more data you have, the better you will be at machine learning. It doesn't matter a huge amount what you throw at it. But most people do not exist in a reasonable level kind of understanding. So there is some level which you do need to be aware of this. But this is the cruel truth of a lot of machine learning. The reason why Handley works so well is because they have the whole internet to train on and most of the world's computer resources to train it. So when we then move on to, after having acquired the data, we basically use our pandas and matplotlib skills to explore any idiosyncrasies that we might see. We'll do that a bit in our workshops. And then there's a general kind of period of preparing the data and using, and this is where you would use scikit-learn to clean and transform the data into a performance. So for these two we'll be covering, and at the end there's this bit of where you actually put it out into the real world and you need to make sure you keep monitoring and maintaining it. For researchers this would be sort of distributing it via GitHub or something equivalent, and for industry this would be sort of shipping it to the real world. So within this rather broad thing of machine learning, we have several categories, the main two which are supervised and unsupervised learning. Supervised being where you have data points that are labeled, i.e. inputs and outputs, and you're trying to find a mapping between those inputs and outputs. And those generally take the form of either regression, which is where you're trying to predict a real number or set of real numbers or continuous variables, and classification, which is where you're trying to predict a set of classes. So regression would be trying to predict a future ocean mapping of temperature, which is a continuous variable, whereas classification would be trying to predict whether it was sunny or not that day, or whether that something was a cat or a dog. Unsupervised learning is basically the classic example of unsupervised learning is clustering, but there's a few other things that fall into that category. But clustering is where I hand you a lot of data and you want to analyze this is a set of anomalous results, or these things are not like the others, and you generally try to do that. And there, you don't give it any labeled output, you just say, find me some patterns in the data. So that's also quite useful for dimensionality reduction. These, whilst it's very easy to put these two in two clean categories, they usually feed into one another. So you will often do a dimensionality reduction to compress your data into before putting that into a supervised approach. And then these other ones where semi-supervised and reinforcement are less of a big sort of blurring the lines between the two with semi-supervised, where you sort of have something that starts off in an unsupervised fashion and then moves to supervised training. And this fourth class of reinforcement learning doesn't really fit into those other ones. Does anybody know what a generative adversarial neural network is? Can anybody describe that for me?
One network learns a pattern and the other one tries to decode or fool the other network.
Yes.
So it's an adversarial situation where both of them are game playing and have an opposite loss function, essentially.
Right.
And by trying to fool the detector, the one network gets better and better.
Before I start repeating everybody, can I assume that people can hear online, or shall I repeat?
You need to repeat.
Yeah. So I'll repeat.
This does kind of capture it a little bit, but yeah,
So
I should have used the microphone, sorry.
Paraphrase, which is a very good description of generative adversarial neural networks, these GANs that came into the fore around 2019, where basically you have two neural networks, one of which is designed to produce images of, say, faces, and another neural network that is designed to detect which one is a fake face and which one is a real face. And you train them up together and you get two networks at the end, one of which is very good at producing faces and one of which is very good at recognizing fakes. And if that sounds tricky, it is, because you can go very wrong as you train two things separately. But again, a lot of this kind of adversarial setting of where you have things sort of playing against one another and learning off each other rather than learning from prescribed data sets is something that's a relatively new bit of the field.
They did hear that online, by the way. So.
Oh, they did.
As well.
Excellent. Bonus. Assume that people can, but do try to speak up if you do want to speak to the audience. And feel free to stop me if you have any questions or anything else on the way. So within those four categories of styles of machine learning, you then have the way in which you train them, which could be batch or online. Batch is where you learn offline using all the available data and then ship it and it then needs to work. So you use this if you're using machine learning on a Mars rover, for example, where it's not able to store anything, not able to store that much data online, or if you were sort of trying to train on all of the pictures of the internet, again, you wouldn't want to put that into a smartphone in order to do that. Whereas online training is where you are able to train and update on the fly, which obviously is, in principle, much better, but is harder to equip a lot of the modern algorithms with. A lot of the modern algorithms need huge amounts of computing resources to train and huge amounts of data. But it's also quite useful for this other term, which is called out-of-core learning, which is where your data set is too big to fit in memory. If you have 10 trillion, if you have 10 terabytes of data, you're not going to be able to load that onto a computer to train all at once, so you have to be able to do some level of updating and on the fly, which is from there. And then here, and kind of the split between this talk is you have the old style of machine learning, which is basically instance-based learning, which is where you learn by heart a similarity measure. So that might be sort of, if you imagine sort of a set of instances sitting in some space and defining how close something is to it. One very basic way of doing machine learning that actually is surprisingly good a lot of the time is to just ask, well, I've got a set of images from the past, and I've got a new image. Which one is that closest to? And let's just call it that. That would be a way of doing that. And then sort of variation of that give you instant-based learning. Whereas model-based learning is what we're focusing on here, which is where you build a parameterized model of the data, train it, and then use that to train the model to make predictions. So in some sense, that's kind of moving back to a more scientific way of thinking about it. It's just these models are extremely flexible and not physics-driven, but sort of driven by some non-parametric capability. Okay, before we move on to the next stage here, we've got just a couple of general challenges that you might find in machine learning. The ones that we're going to focus on are bad algorithm and bad training, but of course, you also need to make sure that your data are good enough. So you can you don't have enough data, then you're not going to be able to do anything at all. If the data aren't representative, which means that they only there's been some subtle collection bias in how you collected it, that can give you enormous problems where it just basically reproduces the data as given. And of course, poor quality data where there's outliers and noise, or if you give it irrelevant or poor features, again, where sort of if you give it things that have nothing to do with the problem at hand and it tries to learn from that, the best it will do is learn the noise, and the worst is that, the best it will do is just kind of add baggage to it, but the worst it can do is then learn noise that's wrong. Okay, so if we go to this, I'm now going to play the most dangerous game of trying to do this alongside with you. So if we go to this website here, and that should give you most of the things that you need. So you can see on this, let's go there. So here, if you go to this website, you should get here. So it's github.com, Handley-lab 2020 Cambridge ICCS.
The link is on the summer school resources page as well.
The link is on the summer school resources page as well. You can download the slides if you want to peek ahead. You can also download the notebook or the script that I use to generate the notebook. So we're going to start by keep playing this. I'll just check that I can do the whole thing with you. So. That way you don't have to. So once we get cloned, we change directory into that, and you should then see there's a few things where there's a few data sets with London weather, example data, a README that's from the GitHub README, and then the various things here. So we then need to go and install the various things. So I don't want to impose any kind of installation procedure on you, but basically to do this, you need to have Jupyter Notebooks, scikit-learn, TensorFlow, and PyTorch installed. The TensorFlow and PyTorch, if that takes a while to download, you can start with that later. So you can do this later. So for now, you just need to install the notebook and the scikit-learn. But for now, I would usually do this with a virtual environment. But Conda is another way to do it. And I'm sure we can all quote a certain XKCD slide that shows how bad Python can be in various settings. So I'm going to do it with virtual environments, which is the older school way to do it, but it's less. So a lot of Mac users will prefer Conda. So basically, you set up a virtual environment, you source that, so source my bin activate, and then that then gives you here on my terminal I have this thing which is my VM, but this is in principle a completely clean install. So if I were to go pip install notebook, that then works, and it will install a Jupyter notebook and everything else into that virtual environment and everything else, and pip install scikit-learn, and this here should, in principle, install both scikit-learn and all of the other things beneath it in the stack. So NumPy, you can see it's installing, and SciPy and Panda as well. Thought it might have done. No, you should also install Pandas. But again, this program parent isn't anything there. And the only other thing to do is if I
I get an error installing PyTorch, just install Torch instead.
Yes, it should be pip install Torch rather than PyTorch. I'll upgrade that now.
And while you're editing the source line,
Yep.
the virtual environments line install you.
Thank you very much. Anything else?
Not yet.
Cool. Yeah, so it's Torch rather than PyTorch. Again, whilst you install scikit-learn, you import it with sklearn, so there's a lot of inconsistencies in Python naming. And then in principle, we can then, once we've done that, the only remaining thing that needs to be done is to tell the notebook where your kernel is. And this is possibly the most subtle thing about virtual environments, where basically I say, my VM is somewhere over there, and in principle, we're then ready to go with Jupyter Notebook. Here we go with training MLOps.py. Okay. Hopefully everybody can get to that point. Has anybody really struggled to install those things or not have them installed before? Any issues?
Fine.
Just as a general recommendation, make the font bigger.
Here? Or in here?
Both.
Here's a harder. But now, we probably don't need my command line to know what we've got to here. Can we read this?
Could you make it one click larger?
All right. So in this first bit, there's a few things, and I put in a few optional exercises for people that are ahead of others and other things. But the general idea here is that there are a set of questions and things that we can go through one by one, and people can have a play with various different things. I'm happy to come around and help people install things if that's any difficulty before, but I would recommend people having a read through this now, and then we can rejoin in a few minutes' time with where people have to think about what the answers to these questions are. Yeah.
I have tested the instructions from the readme, and I think this is also missing matplotlib.
Okay, so we need matplotlib as well. Is that not installed by default in the install cycle?
Yes, I don't think mine installed it by default.
All right. So we need to say we need.
Yes, but matplotlib is annoying, but not matplotlib itself.
Matplotlib. What else do we need to be installed here? Cool. Anything else? Is anybody having difficulty installing anything? I can see you are having no difficulty at all installing anything without a laptop. Yeah.
Do you want that MacBook?
I would want that MacBook.
Dan, do we have that?
Jacob's
Oh, okay. Sorry, so it's on its way.
Okay.
Would you write the website on the blackboard?
Can I write the website where, sorry?
On the blackboard, where I can find this?
Ah, sure, sure.
If you go to the summer school website, it's in the resources, link from the resources section.
Yeah, so this one here, is that right?
Yeah.
All right. So, do let me know if you're struggling to get anything else installed, but hopefully this should now be those teething problems are ironed out. We've got now this thing here. Well, first of all, we start by importing NumPy. We then load the data. If you actually were to look in this example one, data CSV, it's just a two-column format, and this just uses NumPy's load text and transposes it to get to the X data and the Y data. and then we plot with matplotlib to give you these data points here. And you can kind of see that there's a trend, and the eye probably picks up on some kind of extra bend in that as well. So we start by defining our model function. Does anybody know what f defines here? Can they see what f defines here? So x here is data as a rule, and theta is the machine learning convention for model parameters. Is that a hand up?
Yes, we're defining a polynomial.
Yeah, so this is a rather opaque way, or somewhat opaque way of defining a polynomial. So you can see what we do here is we define this I equals np.arange length theta. Arange is just an array that goes 0, 1, 2, 3, 4 up to the length of theta. And then here, you use this here where you raise it to the power of I. So this will take x and raise it to the power of an array 0 to n, which would therefore be sort of x to the 0, x to the 1, x to 2, x to 3, x to 4. And this rather fancy stuff is this advanced numpy that I was referring to earlier, where we basically use an ellipsis to say as many things as you like, and none to do this rather fancy broadcasting, which is where you basically take an array x and allow it to be able to broadcast across these two here. If you haven't seen this before, I wouldn't worry too much, but all I'm saying is that numpy, when applied well, allows you to do a lot of very powerful things without you using C++ or anything else. Does anybody know what the none slicing does, if they were to describe it? Has anybody seen that before? No? Okay, is there a blackboard? That's probably a good way to. And is the blackboard being filled? Is the blackboard being
This
filled?
one is.
Yep, we can see that.
Is there light?
I'll tell you, it's sort of, yes, there's chalk all on the right hand side there.
Down there, can you turn on the light a bit more?
Yes, I can do that. I think you can go to about here.
Yes, it's hard to reach.
That's the one for the leftmost.
Yeah.
Yes, that was it.
No, I think there's another switch over here.
Okay, so one way to think of this is that in the past this would have been defined by np.newAxis, which is where you say, I want to, so here's one way of defining this, which would be to have a slice and then an np.newAxis that you then raise to the power of I. And the idea here, this I, which is already a vector, then applies to its nearest axis under numpy broadcasting rules. None is something that was applied recently, which means if you put none there, it interprets that as a new axis object. And the ellipsis is something that gives you as many things as you want. Can anybody see why you would want to do this? It's probably a better question. Because if we take f, we can then look at f of x, and then that would take in all of the x values from this array and fit something that is 0 plus x plus 2x squared into that. So if we were to plot that, that would give us this polynomial here, where you see here we've defined this as 0 plus x plus 2x squared. So if I change that to minus 1x squared, it then goes down. If I would change this to minus 1, it will shift the polynomial to the right. So that's what this is doing here. So that's our theta, which is piped in here. This then turns that into 0, 1, 2, and raises that to the power of that and does here. But can anybody see why this is advantageous in this setting. This is all the advanced number we're going to do. It's just going to give you a flavour for this.
So someone on the chat says it adds a dimension?
Yep.
Question mark.
So yes, it's definitely about dimensionality. So for example, here, if we go back to this, so away from the plot, and look at what f of data x does, it takes in a vector and gives you out a vector of the same length. But if I were to give it a, say, another set of numbers, mp.random.rand 10, 20, this thing here, call that x, will give us, first of all, if x is a thing of shape, x, there we go. So x will be something that's of shape 10, 20, and if I pipe that into f of x, it will produce something of shape 10, 20. And in general, this would work for an arbitrary length array. So I can make this 10, 20, 100, and it will still give you the same sensible output and give you this. So this kind of way of thinking about this, and this ellipsis, is a way of writing functions that can take arbitrarily complicated NumPy arrays. So as an extra exercise, if you think that's easy, try writing it so it can take arbitrary theta arrays. But for now, let's move back, get this away and move back to where we were. Finally, what does the np.array line do? Anybody know? Why do we need that line?
So that we can pass in Python list or something else and convert it.
Good, so anything array-like will become that. There's also the final corner case, which is ideally we would like if we pass f of just a number.
That promotes it, does it?
It promotes it to not an array, but a scalar, which is one of these things which normally looks rather annoying, where you have np.array5 without a list. Array5 without brackets rather than array5 with brackets. It's one of those things that normally looks a bit weird, but the reason why we want that is that way NumPy is clever enough to interpret that to do the right thing, like to treat it like a zero-dimensional vector. So there's a lot of things there that were in that line, and I encourage you at the end to go and try to understand this, because if you can master these tools, that's kind of like this is black belt level NumPy if you know what you're doing here, basically. So equally you don't need it, but there's a lot of things you can do there which I would recommend, and that's all we're going to do with that for now. We can do this. Okay, the next stage here. Who here has used scipy.optimize.minimize before? What does it do?
Minimizes the function that you pass it with some arguments.
Yes.
And use the arguments that minimize the function.
Yes. So it minimizes a function. So you give it a function, and you give it a starting point, and it says, find me the smallest value of this function from this starting point. So can anybody see what we're doing with this function here?
Someone from the chat has got their hand up, possibly to answer that question.
Yep.
Kenza, do you want to unmute and...
Oh, sorry, I was just answering the question how I used scipy.minimize before, and I think somebody else has asked.
Great. So that's a yes then?
Yes.
That's super.
Yes, I have answered it. Good. So can everybody see what this loss function is doing? Mean squared error loss, exactly. So this basically takes the prediction, f of data theta, which is this previous function here. So it takes in all of the data points and some set of parameters, subtracts off the actual data we saw as output here, squares it, and then sums it. So this basically is a chi-squared-like term where we're doing a chi-squared-like fit. This is a very manual way of talking about it to introduce us to the next stage of how we think about these in neural networks.
Where is the data x, data y? Where's that bound? Is that like a symbolic thing? Oh, okay.
So these are just loaded in at line 2.
Great, thank you.
It's these data x's and these data y's. It's a very good question.
Yeah.
So and again here we're using Python's ability to know about things globally once things are defined. So they're not defined. Yes.
Unnecessary nitpicking, but you're missing the mean part.
Oh, so between sum versus mean.
Yeah, it's 1 over n.
Yes. So does anybody? So we could either change this to mean, or change this to sum and divide by len of data x. Does it matter?
No,
Why does it not matter?
because the minimum of that function is the same, is effectively rescaled.
Yes, so mathematically it doesn't matter whether we do the sum, the mean, the square root, or any other monotonic transformation of this function because an optimizer does this. This is true up to a few caveats. In general, you want this number to be a sensible number. It shouldn't be hitting floating point precision or going through a huge dynamic range, things like that. And ideally, optimizers should be invariant to such things, but they are not in practice. They do use a lot of things where they assume that this is defined in a reasonable way in some kind of metrical space in a way that's hidden. But that's quite a technical point. Okay, so this here is we have defined a start point that is basically 4 zeros. So it's a length 4 vector with 4 things here. I minimize that, and that gives us a solution. If we look at what the solution is, that gives us this answer here, which says that, okay, we found the value of this mean square sum. If we change it to mean, we should find that it comes to 0.83, which is the mean square loss, and you get this x is your answer out. So it's 0.78 plus 2x minus about 3x squared plus about x cubed is the kind of the answer here for this thing here. And if we plot that, that's hopefully what it should look like. So this here is an answer to this problem. So this here is us kind of fitting that here. So all we're doing here, this plotting is extracting sol.x to get that answer out there. You're then plotting the data. You're then defining a new x variable here that's just a smooth thing here from -1 to 3 with this np.linspace. And then you are plotting the answer out here. How would we do this to fit? How would we change this bit here to fit a quadratic function rather than a cubic function? And we see what we would change in this code.
So in which code?
Either
Any.
of these two cells.
Turn theta 0 to empty 0 is
3, because then that would be 1x squared. So that gives a quadratic fit, and hopefully that should give us something that is nowhere near as good. Interestingly, it doesn't even look that quadratic, but if you check what the solution is, it has a very, very small quadratic term. So it's basically the best it can do is something that's very close to a linear fit. Okay? What will be the next natural thing to try?
5.
Try 5 and see what that looks like. And again, it again looks pretty close to cubic because the higher order term, the quartic term, is also very small. So let's have a look at this. And then this cell here just does that of what we did there, where you've got sort of the constant fit, the linear fit, the quadratic fit, which is missing, the cubic fit, and the quartic fit. Where is the quadratic fit?
Orange line? No, the red line.
So the orange line would be the linear fit, would be the constant fit, and
That's the red, red one.
so they overlie one another. Again, it was this kind of idea that when we tried to do a quadratic fit, we found that the x squared term was virtually nil. Okay, and then here, if we plot that, what have I done here? I've set this to 10, and I get this as our answer. Can anybody see what's gone wrong here?
Too high order. Lower bit.
2 high order overfits with those two answers. What do you understand by the term overfit?
It's fitting the noise of the data as well as the data, basically.
Fitting the noise in the data as well as the data is a very good sort of way of expressing that. And ideally, you would have a way of telling a model not to do this, and this is what we're going to discuss later on. Okay, other exercises are to plot the loss as a function of n, and to have a think about how we can go about choosing n and programming something if you have time. I'm conscious of how much time we have, so we're 45 minutes in, and ideally, I think we get to sort of exercise 2 within an hour and a half, as in within sort of the next hour and a half, and then we've got the half an hour after coffee. Is that right?
Well, yeah, so 45 minutes, then a half-hour coffee break, and another half hour after that.
So I do encourage you, if you are bored during my talk or otherwise, to fiddle with this code. It is there's a few things that you can play with and get an understanding of what's going on here. but this is kind of introducing the elements of trying to fit data using just a scipy.minimize function. And at the bottom, I've got the code that I used to generate it. So the correct answer was a cubic polynomial that I set up here. So. Okay. Moving back to here. Right. So the general structure of training a machine learning model can be found in this. But basically, there are 3 ingredients to training any machine learning model. You first of all start with input data, your features X and your output data Y. Here the input data was just a one-dimensional thing, but in general this would be a many-dimensional thing. You can consider a parameterized model, which in our case was that rather sort of fiddlily defined polynomial, but in general could be anything from a decision tree to a neural network. So some way of parameterizing model where you have it taking in data X and depending on some parameters theta and producing a output Y, and then a loss function, which basically compares its predictions with its answers to give that. We then train the parameters on a training subset of data by solving the mathematical problem we did just there, which is where you minimize some loss function with respect to theta to get out some fitted parameters. And then there's a second stage, which we also discussed in some small detail, where you then try to choose the best model. And here we got to the stage where we were considering different models or different polynomial orders, but didn't really discuss how to pick the correct model, which is then done by choosing the best model by minimizing a possibly different loss function on a validation subset. And then finally, you would test the best model with set-aside data. And we're going to unpack this over the next few slides. So the first instance, when you are picking your data, the initial data must usually be transformed and the relevant features should be selected. So what I mean by that is that, that if you are trying to fit some set of data to some other set of data, some things will be completely irrelevant. So for example, if you're trying to fit rain, the number of lectures on that day probably doesn't depend on fitting rain, but it would depend on, say, sunshine or on whether it's rained previously. Picking the correct features is known as feature engineering, which is where you sort of try to either pick features or produce features that can be by computing rates or sums from other things. And this is generally where a lot of the work of a data scientist would have lied back in sort of 2010. Features should then be normalized, and this is a critical part of all machine learning pipelines. You do need to make sure that the data going into it are dimensions, because in general, almost all machine learning algorithms are not covariant, which is the correct way of saying this. It matters whether something is measured in meters or kilometers or picometers. If you put in picometers into something, it will give you, it will bias the answers in an odd way. So usually, you need to normalize this data and transform it. And scikit-learn, as we will discuss, has a lot of tools for doing this. Instead of you writing these tools yourself, where you min and max scale to 0 and 1, or you standardize by ensuring that the data going in all have mean 0 standard deviation 1, these can all be done by using these sklearn pre-processing things. And this sklearn pipeline is also a very clever way of chaining all these together. So I would say that if you're writing your own machine learning pipelines and codes, understanding how these fit into this can save you a lot of pain and allow you to reuse things very straightforwardly. So I recommend these as tools. Choosing the models would fill a whole other session. Here's a list of things, some of which you may recognize, some of which you may not. And these are all sort of taken basically from scikit-learn's suite of things it can try. We tried a polynomial fit, and we will see some decision trees and random forests later. But really, all of this stuff here, where you talk about k-nearest neighbors or logistic regression or support-based machines, this would fill another talk. And again, unsupervised clustering is something that we don't have time to discuss today. Neural networks will form the bit after the break. Okay, so, and the third portion of this, when we sort of had our list of data model selection and loss function, is where basically you need to compare this. And we described the mean square error, or the sum squared error, or the root mean square error, all of which are basically the same. The other thing which is different, which we could have chosen, is to take a mean absolute error. And this is better because it's more robust to outliers. If you have something that's a data point that is very, very far away, a squared error makes that, gives it a lot more weight than just a differencing error. And a Huber loss, which aims to combine these two in it. It gives you the smoothness of a mean square error whilst also being robust to outliers. In practice, this is not usually something I would twiddle. you might like to justify to yourself mathematically it's the case, and in fact that given that these match up, what I've really plotted here is a half delta y squared rather than delta y squared. Okay. So one of the key principles of training, validation, and testing is that you should take your data and almost immediately you should set aside 20% of the data for testing at the end, that ideally you would never look at until you're absolutely happy that you've chosen your model correctly. Within the then training data, you would then usually split that into training and validation subsets. And in fact, you can cut and slice that in many different ways to kind of test this whilst you're trying to learn hyperparameters. But in general, the fear with any machine learning algorithm is that you overfit by choosing a set of parameters that fit a model very, very well, but actually the moment you try to do something new, because you've been fitting noise, give you a completely erroneous response, like we saw with that curve that was very sort of unusual and was clearly not sort of a very physical model of that data. This is very, this matters a lot. The thing that a lot of people tend not to consider, there is a third level of training that people tend to forget about, and this comes down to this testing element. You really should ideally make testing a one-shot piece of data, and the people with lots and lots of data will be able to actually, if you're faced with, you can discard things and use them genuinely only once ever, because there's usually another for loop, which is the human for loop of trying lots and lots of different things. If it fails, trying again. If it fails, trying again. So the testing data should really be held out and only sort of tried at the very end. In practice, usually it's quite difficult to have truly one-shot data, but the data is quite valuable.
Sorry, by one shot you mean you only use it for testing, you don't?
Once,
right.
and then never again.
Okay.
And if you then go back and change it, you should ideally have a second set of testing data. In practice, that's something that only people with virtually unlimited supplies of data can do. But that idea here, the idea that the moment you've tested on that data, you've moved it into science, so that when you then go and say, oh, well, support vector machines didn't work very well, let's move down the list and try decision trees and try that. You will only stop when you get a good answer, and you effectively put another for loop and brought that testing data back into some. So the human for loop is the one that people forget about a lot of the time. And ideally, you should therefore do all of that on the training 80%, leaving the testing until immediately before shipping. You get this in cosmology in the context of blinding, which is where you have similar things where they do all kinds of things where they sort of design their code such that you don't, you know that the answer that you're going to get out is an obviously wrong one. We'll come into blinding later, it's probably an aside, but this training validation testing is very important. Other gotchas you need to be very careful of is that if you're doing any of this standardization and normalization, where you sort of normalize to 0 and 1 or to unit mean, you should only use the training and validation sets to do that, and make sure that you don't use anything in the testing set to normalize, and because otherwise it's not generalizable. You're effectively peeking at the data before you start. And ideally, again, the splitting procedure should be random seeded, so that when you do this 80% 20% split, you should not just click at one end of the array unless you've already shuffled the array. And if you shuffle the array, you should make sure you shuffle that in a repeatable way such that when you add in new data, it doesn't completely break everything else, because you might find you want to take them out. And the way that you get the way that you get all of that for free is by using sklearn's train test split that we'll see earlier. It does a proper, random, seedable, repeatable, reliable, and sort of sensible way of doing it. So I'd recommend the train test split that we'll see later as the way of doing this. There's also a thing called stratified sampling, which is where you want to ideally make sure that your training and testing data are similar enough in the thing that's critically important. So i.e., you don't want to, in doing this 80% 20% split, you might find that if it's a small data set, you by chance get a lot more women than men in the data set, so you end up biasing results to men rather than women, or so on and so forth. So stratified sampling can be quite useful, but again, it's something you should be careful and cautious of using. Okay. So let's discuss how gradient descent works, which is basically how that scipy.minimize tends to find these answers. So to minimize a function, you start somewhere at theta naught, and you go downhill one step at a time using the derivative of the function. So in 1D, the derivative of the function just tells you which direction and how fast to go in, whereas in several dimensions, it will tell you which direction to move in this higher dimensional space. So in the polynomial space, where we were fitting the coefficients of 1x, x squared, x cubed, x to the 4, you will be adjusting those using that gradient. How can this go wrong? Or rather, in this simple algorithm, what haven't I specified that could mean this could be a bit off?
Eta?
Eta. So if I specified eta incorrectly, what might happen?
Either you're gonna sit there for a very long time, or it just jumps over the minimum.
So if you choose eta to be too slow, it will take you a very, very long time to get that. So if this eta number here is too small, this is called the learning rate, then it will take you a very, very long time to crawl to the bottom. And if you set it too high, you might find that you either overshoot and you end up getting into these rather odd patterns here. These are real things on this real function. I've got a little Python script that does this. Where else can this go wrong?
There could be multiple minima.
There could be multiple minima. So you could find that there is this thing here, and all we're doing here is bouncing around something that is not the true minimum of this function. And in reality, we want to start at some different point theta naught to get there. And again, within that though, there are other things that go wrong. Where else might this function fail? Or might this approach fail on this function that I've drawn here?
Or the flat bit.
On the flat bit. And if you put it there, it's not going to go anywhere because there is no gradient, it stalls. So these are basically the various problems that go wrong. And for all Glorot and Hitchy initialization and all this kind of other stuff that goes on later with the neural networks, it all comes down to this basic principle. The gradient descent can get stuck in local minima. If you set the wrong learning rate, it will take a very long time to get there. If you set it too high, it will just keep missing the minimum, and it can get stuck in a flat bit. This is basically the main points that all go wrong. Okay, let's go back to the notebook. So here, I downloaded this data from Kaggle, which is a very good website for basically fun testing, training data sets. And this is data from the London weather, and this is going to be a showcase of pandas, which hopefully should work, since I should have the same installed now. So here we import pandas, we read this CSV file, which is something that Excel could read or otherwise, and here this data.h just looks at the first 5 rows of that. So you can see here in the iPad notebook, we get a rather nice sort of pretty HTML picture of this stuff here, and you can see that this data set has a date, written in a rather unusual, basically string. It is an integer, but it's 1979, the 1st to the 1st, 1979, the 1st to the 2nd, so on and so forth. The cloud cover, sunshine, global radiation, minimum maximum temperatures, the mean temperature, how much it's been raining, and what the pressure was. So you can see here, immediately there's a lot of different dimensions. This here, almost a nonsense dimensionality, because this is barely a date, because it will go up to 30 and then jump to the next one. This pressure here is measured in obviously a sensible physical pressure, but it's got 10 to the 6 as its units, whereas the radiation is measured in tens. Whereas these things here look more normally, relatively normalized. Just to showcase some of the pandas, data.info is a useful thing just for sort of getting this information out about what we have, date being an integer, cloud weather being a float. And data.describe is a very useful bit of thing that just basically gives you some stats of this data. So you can see that the pressure has a mean value of 101, and the sunshine has a mean value of 4, the precipitation has a mean value of 1, and all these various other kind of things that go down there. One thing that we'll notice is that the count, which rather than helpfully is float rather than integer, you have 15,332 for cloud cover, but only 13,900 for the snow depth. And these are therefore down to missing data. There's data not there. Pandas is extraordinarily good at dealing with missing data. It's also extraordinarily good at dealing with timestamps. It's one of these things where I have seen some of the die-hard Fortran programmers that I know that will never use anything but Fortran see Python's merging of timestamps and go, well, that's just crazy. There's something to do this well. So Pandas is a very, very powerful tool. Warnings are it is sometimes too clever for its own good. You can do a lot of things with re-indexing and things that you're not careful of. So it's worth mastering Pandas, I would say. We could do lots of things for this missing data. We could, for example, impute them with this sklearn simple imputer, which is basically when you fill them with the median value or fill them with nearest neighbor values or things like that. But for now, we're just going to drop them here, which is just drop NA in place equals true. In place equals true is another very important thing for Pandas. So, Pandas HIST method is quite useful. Just about readable here with this number of variables. You can see here you've got the date, which runs from various things. Very well. But it's quite a powerful tool for quickly giving a feel for these things. The interesting thing for sunshine and precipitation is that 0 clearly features relatively heavily in these data sets. See there. So this is what the precipitation bin looks like. It's a pretty zero features fairly heavily in terms of fit this, and it must be positive as well, which is also worth knowing. Okay. If we look into correlations, we can use data.core and then extract the sunshine column. So if we just comment that out briefly, the correlation matrix looks like this. So here, this is something where you can look at the correlation. So data is obviously perfectly correlated with itself, as it's, it's all down the diagonal. But here you can see that sunshine is correlated with global radiation pretty highly, and actually with a fair number of things, apart from the date or the snow depth. It's interesting the snow depth does not correlate with sunshine that well, because you'd imagine it'd be a pretty sort of one-shot thing. But the correlation is a very linear way of thinking about data. So ideally, with this machine learning stuff, we're trying to get to non-linear ways of approaching data. Right. Scatter matrix is also a fun one to plot. It takes a bit of time to think about it, but we eventually get there here. And so here you can see this is the equivalent of that correlation matrix, but with scatter plot. So down the diagonal, you can see the normal histograms instead of perfect correlations, and down off diagonal, you can see basically precipitation and otherwise against everything else. If we were to select a subset, say precipitation, mean temp, and max temp.
Precipitation means.
Thank you. It's the data that I'm in the wrong place, and I spelled wrong, so I should put that there. If you see me do anything nonsense, do shout out. Work. Now here, this was my spelling error, is that right? Precipitation. This is where I'm missing my bin autocompleter. What else am I missing? So that's, now this is here where I need the look. Let's not try coding in front of people. For now, no need to do this. Okay. The other thing that's pretty useful here is being able to define new columns. So we described the date as being a pretty silly thing to try, but here what we can do here is we can define a new column that is the month. And this is again where Pandas is extraordinarily impressive, where you take the date column and you say, okay, it's year, month, day. It's often you don't need this, it's very good at some auto formatting that. Okay. Sorry.
So it's just backtracking a bit. So you dropped the NAM values, which you said were mostly missing snow depth.
Yes.
How safe is dropping those values if they are correlated in snow depth in particular? As in, could it be that snow depth is missing on several days for a particular reason, maybe because of hot weather or something else?
It's a great question, and one of the things I would encourage you to do is to try that out. And maybe perhaps instead of to test the hypothesis, you could try replacing snow depth NaN values with zeros, assuming that NaN value means there was no snow, which would be a reasonable thing to do. I did try it; it makes very little difference. But if you want to give it a go, that's exactly the kind of question we should be thinking about here.
Thanks.
Okay. And if we then look at sort of this thing here where we take the date, format it, and then use this pandas functionality of .dt, which is basically just to extract the month, that then gives us the columns of integers for that. And doing that, we find that, interestingly, the precipitation is relatively month here. We can see that month is actually not very well correlated with anything, which is unusual, but of course, if you think about it and plot what the scatter matrix looks like, the month correlation will not be a linear one. For example, here in the month column, you see that it goes through these cycles, and this is the thing that, again, a correlation analysis or a usual linear regression would not pick up, but a machine learning approach like scikit-learn would be able to pick up. So I recommend those. Again, we'll drop the month columns for now and come back to that, but we can can start again commenting that line out to see how big a difference month makes later on. Okay, so now let's look at scikit-learn. We extract, we're going to try and predict the amount of sunshine to start off with. Sunshine, yeah. And extract the sunshine column and drop sunshine from this. So this again is very standard machine learning terminology where Y is written as the data for the thing you're trying to predict, and capital X is the matrix of values that you're trying to predict from. You might want to look into using stratify shuffle split if you're fiddling with the code yourself at this point here. But for now, what we're going to use is this train test split, which rather magically takes, if you just take train test split and you give it X, Y, and test size 0.2 and random state 42, it will split these up into X train, X test, Y train, Y test. I'm not sure how to cite that.
Is random state setting the seed?
Yes. And a few other things, but yes, it is. I didn't do this, did I? Yeah. Okay, I better restart the kernel. Okay. Background. Has anybody else been able to run this alongside with me and got to this point in the code? Yeah. That's what I want. Is everybody else working? Is nobody else working? Are you able to? You are. So this is my. Right. Pardon? One could use. I use content rank.
I was okay with that.
No chance of anything to sandbox if you're using virtual.
Probably yes. The other thing I can always do is just switch back to my home system. But let's do that on the cookie break for now.
Oh, do you have it installed on your? You can use Archer if you have that installed. That's how it works. That doesn't sound.
This will work. Okay, backtracking here. Right, 20 minutes until coffee.
We don't have to do everything.
I know we don't do everything. I would like to get some neural networks in there, so I think so. We're nearly there. Okay, scikit-learn is working. Now, if we and here we can see we split into xtrain, xtest, etc. And you can see xtrain now is a vector here, where here instead of it being shuffled in terms of 1 up to here as before. So where previously the data would have looked like this, where it goes 0, 1, 2, 3. You can see here it is shuffled rather randomly, but in a way that is reproducible with random state, which is somebody pointed out was a seed. Okay, we then transform that, and we can now go. So yeah, here's the meat of this. Here we do sklearn pipeline, import pipeline, sklearn pre-processing standard scalar. What we do here, and this is the general philosophy of scikit-learn's stuff. So this is possibly an important thing to take away from this talk. We define a standard scalar pipeline. You then fit it to xtrain, and here the fitting is a relatively trivial thing where you just compute a mean and a variance and use that to define the transform function, which then 0 means and 0 variance is the xtrain. So whereas previously you might have written this yourself where you would write x_train minus x_train dot mean over x_train dot stood, which would be one way of doing this. Depending on how vectorized it was, you would then need some axis commands and otherwise. This here does that same thing here, only importantly, if you were then to use this on the testing data, you would need to transform the testing data using the training data's mean. And this way of thinking about things in terms of pipelines where you fit them to the training data that you then apply to the testing data is a very powerful and consistent way to think about things. It's actually the same framework that you would then use to fit your linear regression model or your other decision tree regressive or things like that. So you basically think about the whole transformation pipeline in one go. So I would recommend this bit here is possibly a very important cell to think about and understand. The pipeline itself as well is at the moment just a very simple standard scalar, but you can do a lot of other things using min-max scalar and this sklearn composed column transformer, which is again a very powerful thing for defining your own transformations. Okay, that, we get to here. So in this point here, we define a linear regression, which we fit to our transform training data, and then we do this. I recommend that you work through this here yourself, basically. But basically what we find is that linear regression does an okay job, where you get to some outliers here, and a decision tree regressor, which if you basically take the same stuff we did here with the linear regression, and defining the mean squared error to give us this, we get to this as our prediction of input data and output data. If we do a decision tree regressor, we get something that looks like this. And this here is an example of being completely overfit. It's fit everything perfectly within the training set, but obviously that seems fishy, and we should be thinking about, can we ask how well this generalizes outside, and then the lines for cross-validation in scikit-learn just look like this, where you have scikit-learn model section, import the cross-val score, you apply that, and then that here gives you these out-of-sample scores, which basically says that it's doing actually slightly worse than the linear regression model when you look at it out of sample. Not lots worse, because the linear regression model is actually not doing that well, but it is doing worse. The next thing to try then, which one could try, if we had more stuff here, is a random forest regressor, which is basically a stack of decision trees. And if we do that, it no longer gives an answer out that comes out as 0, it comes out as 0.4, which is reasonable, still possibly a bit good, and gives you this. So interestingly, so this is in sample, and then out of sample, when we look at, again, the cross-validation scores, again, this is all, what this notebook is mainly made to show you is that there's a set of key tools you can keep reusing that people would often write themselves, that is not, that you don't need to if you understand the nuts and bolts of scikit-learn. Okay. And the random forest regressors are a little bit more heavy duty than the decision tree, so it takes a little bit longer on this laptop to do it, but it's running that HDMI. There we go, and we get to this here, which again, this now is looking better. So if we were to plot them against one another, you can see that really the reason why this is doing better is that it's finding, it's kind of removing this set of outlier points, so it's learning that. This here is what we're going to talk about later, which is how we can tune hyperparameters by running over a grid of those. Again, if we find that, we can find that this is a way of choosing these various n estimators max features to straight into that. Cool. So it turns out that doing a grid search over the training and validation data, the best things here are to have 6 features and 30 estimators, which are these hyperparameters of this method. And then the best model looks like that, which we can use to basically find our final model, which looks like this. So that there is what our final prediction looks like with having done all this. And this here is the main difference. So it does a little bit better because basically it's good at dealing with these outliers, but it's still not great. It is quite hard to predict sunshine in Britain, is the short answer to these questions. So, one of the things you notice, actually, particularly when you try and construct your own example, is quite how well-rounded all the usual things that people choose. So Boston Housing or MNIST or the MNIST fashion stuff, they're all rather cleaned up data sets in which people have tried a lot of things on. And they tend to act like this is a very easy way to do things and to get to an answer very quickly. But in reality, they've massively overfit a lot of their algorithms to get there. So it's quite subtle, that small point there. But I would recommend having a go with this, and in general, if you fancy reading through this exercise more carefully and looking at these questions down here, like for example, if you change rainfall, temperature, or otherwise, this is a lot of things. Month does make more of a difference than you think, actually, obviously, because how sunny it is depends on the month. So if you add in the month thing, and if we had time to do that, we would get to that. Okay, let's chat in the final 15 minutes on the way up to neural networks, and then we'll have some coffee. So on our So it depends on whether we want to have time to go through some of the neural network examples, whether or not I do this now, or whether we have coffee now and maybe 45 minutes rather than half an hour later.
It depends on whether the coffee's there. Yeah.
I would also point out this paper there. So if you type in that telephone number into Google, it gives you a very nice set of tools on that. Any questions? Yes?
Yeah, could you explain what a decision tree does? Decision tree.
Do you know what a random forest is?
Yeah.
For those that don't know, a random forest is basically a machine learning technique that can be quite good at solving a lot of things by basically doing a lot of if-then decision tree kind of style statements. And a random forest basically stacks an ensemble of those together. It's quite complicated, and if you're pressing me, I would struggle to.
In this particular example, it would say, okay, let's have a look at this variable. If it is something, then it isn't something?
Yes, and that's why the random forest in itself was able to perfectly fit the data, because it basically just learned that on the data that's there. But the decision tree, by sort of stacking several of them together and doing something a bit more, that's actually quite similar to what we were doing with the cross-validation in its own marking. It's a good way of doing that. I do encourage you to have a read of what these things do. It's not meant to explain what a decision tree is and why it is, but what the main bit of that notebook is meant to show is the kind of guards you should be playing and applying to make sure that you're not overfitting, which involves leaving testing data out, using cross-validation, and if you get a really good fit, being immediately suspicious that it is a good fit, because you find that when you look at it out of sample, it might not be. Yes?
What's considered deep learning?
This is my phone.
Oh, sorry. What can you consider deep learning?
So we will get there, but the question is what can be considered deep learning? The short answer is more than one hidden layer in a neural network. Should we get some coffee?
Yeah.
That way it's split better.
And then come back at 42.
Yes.
With
That thing. Yeah. So whenever you read about backpropagation, it's less important than you think, even though most neural network expositions will begin with quite a long discussion about it. Really, all it's saying is that the reason why neural networks work so well is we can get gradients quite cheaply. And all the rest of it is more mythology and people repeating it. It's important to understand different variations on gradient descent. This is important for when you're picking various dials within a neural network. The simple way of computing a gradient, which is just compute the gradient of the whole loss function, is deterministic but very slow for large data sets. One way to speed it up is to basically subsample the data so that you have much smaller amounts of data, and in the extreme case, just do it for one data point, but randomly sampling that data point as you go. This is much faster. In general, it will be of order n data times faster, and the randomness can actually be helpful for escaping local minima. In practice, what people most do is a mini batch form of gradient descent, which is where instead of taking just one data point, you take about 32 of them and use GPU acceleration to sort of compute those quite quickly. So they're not quite as noisy as sort of a completely stochastic gradient descent, but they still get all of the goodness out of it for basically the same cost. This is particularly important for where the data sets don't fit into memory, but you still want to use gradient descent. Another key concept in training neural networks is regularization, which is, not just neural networks, but all machine learning things, is regularization, which is that basically the fear, as we saw with the polynomial, was that if you added too many parameters, you could end up having sort of overfitting the data. So one way to do this is to have models with fewer parameters. The other sort of, if you like, dual way of doing it is to have the same model but to constrain the parameters, and that's what regularization does. You can either do it by adding additional terms that stop them getting too big or getting too variable, which is what this ridge regression does, or you can do something which encourages, when you optimize, things to be set to 0, which is what this lasso regression does, which is other terms you might have heard. For now, it's less important the mathematics how it works than the principle that regularization is the same idea of reducing overfitting by reducing the numbers of degrees of freedom. And again, as with machine learning, there's usually, whenever you have two examples, there's usually a halfway house where elastic net combines the two. And the other thing that you may have heard of, which is remarkably simple, which is called early stopping, which is where if you look at the curve on the right, you have, as you move through epochs, which is basically the number of gradient descent steps, you will watch your error in your training set get smaller and smaller. Initially, sort of, as it finds an original minimum, get quite rapidly small and then start to tail off and get sort of less. So that's what the blue curve is doing. The orange curve is what happens on the validation set, which is that it will go through the same principle, but as you go to further and further down the curve, you start to overfit more and more, which means that the validation set stops getting better and starts getting worse. And in general, early stopping basically says you just look at those two curves and you stop when the validation set starts getting worse in terms of when that loss function gets better. In practice, because it's usually a stochastic gradient set, there'll be some noise in this, so you need to sort of go a little bit further and then sort of backtrack. Once you're happy, you're sort of rising again. But this is one of these things that's basically as close to a free lunch as one gets, in that it kind of speeds up training because you don't need to train for as long because you're stopping early, and it's an automatic regularization that's well tuned to everything else. So early stopping is actually pretty much the state of the art in terms of regularization that people tend to use all the time. And all early stopping is this idea that as you train and as you sort of improve the training, you basically stop when the validation out of sample starts getting worse. Okay, a neural network. You may well have seen these diagrams before, and you may well have seen this mathematics before. The mathematics is less important than the things that will follow, which are the dials we can twiddle. But basically, the idea is that you start with an input set of data, and you've got which are these x's, and an output set of data, which are the y's, and you move them through these mathematical transformations in moving from x to layer 1 to layer 2 to layer 3. And the key point here is that a deep neural network is one with more than one of these hidden layers. So a normal neural network is one with just a single hidden layer, and a deep neural network has more than one. In general, these can get quite deep nowadays, 10 or more layers deep, and they can get quite wide, hundreds of things wide in general. But this is the general picture that you have. And the reason why this is a good thing to do is that, in principle, it emulates kind of how neurons actually work, in that. And you need to be quite careful with this, because this is what was inspired by biology, and actually a lot of the coming of age of this in the 1990s was actually undoing some of that biological bias, where we're still trying to think about these as if they were neurons. But the principle of it is the same. You have inputs coming into a neuron, which fires when it reaches a certain activation level to stimulate other neurons, and then that pattern of firing gives you something that can be responsive and learn lots of different things. Of course, the way the brain actually works is completely different to how artificial neural networks work, in that the brain works at a glacially slow, massively parallelized pace in comparison to these other ones. So we might think we're training deep in big nets now, but we're not. Our brain is also nowhere near as connected as a typical deep network is. So the deep networks we train are completely connected, or if they're sparsely connected, are still much, much more connected than this other thing. Whereas the brain will sort of move at a pace that is, sort of thousands or hundreds of thousands of times slower than a CPU will operate in terms of how fast these neurons fire. But it does it at a much, much more parallelized pace and a much more sparsely connected way. So whatever the brain is doing and whatever neural networks are doing, we're still some way from them being actually similar analogs to one another. But the same principle is true, that this is a relatively generic way to get a way of describing arbitrary functions. So another thing that you hear a lot of people talking about is the universal approximation theorem, which is that any function, whatever you like, can be found to arbitrary accuracy or emulated to arbitrary accuracy by a sufficiently wide single hidden layer neural network. So if you, instead of having these multiple layers, you just have one layer and you make it infinitely wide, you can basically train any function you like. In practice, of course, you can't make it infinitely wide, and these things are actually quite hard to train. So the real question, though, is why do we therefore even need any deep multi-layer networks? And the key principle and insight here is that the early layers in general perform a form of feature learning, where the usual manual stuff that you would be doing by sort of taking differences or taking ratios or taking gradients of things, or saying, well, maybe I shouldn't be looking at the date number, I should be looking at the month number, maybe I should be looking at sort of the overall count, I should be looking at the rate of these things. All that kind of stuff is performed by the earlier layers in various different guises. So that's the principle of what deep learning is. It's not that you need them to be deep to approximate any function, is that you need them to be deep to automatically prepare the data. So all the kind of stuff that would usually require a lot of human intervention, of this feature engineering, is done by the network itself. And again, that principle of the earlier layers doing things that are useful is the principle of transfer, which is where, if you imagine taking those earlier layers, clipping them off, and then reusing them elsewhere, that's the kind of thing where you can train a deep convolutional neural network that becomes very good at learning faces on sort of all of the faces on Facebook, and then take that to a new set of faces or a new set of problems that it's never seen before. And if you reuse those portions of the network, that is called transfer learning. Again, it's a way of getting more data into your problem. In terms of the state of the art nowadays, basically, there are two games in town, TensorFlow and PyTorch. This is complicated by the fact that TensorFlow is usually used with a layer of keras in front of it. So TensorFlow are the big boys and girls toys that they use at Google for like really hardcore computational symbolic math libraries. It's also very hard to use and very hard to understand. If you ever chat to anybody there, they'll spend an hour talking to you about graphs to start off with for no obvious reason before you actually get into the meat of these things. PyTorch is developed later by Facebook and has a much more native feel to Python. It feels like you're programming Python even though you're actually doing something very powerful under the hood. And then there is keras, which forms a, if you like, scikit-learn-like layer for TensorFlow. So keras is actually a very, very straightforward thing to get up and running, but if you want to do a lot of messing around, PyTorch is a relatively Pythonic way to do that. But if you want to do the really hardcore stuff that Google spend their time on, then you would go to pure TensorFlow. And that sort of interplay is quite difficult. In reality, they're all doing quite similar things, and like any programming language, it's possible to translate between the two. And I'm hoping to give you something of a flavor for the differences between these two in the notebook. Keras was originally designed as a Python API for TensorFlow, CNTK, and Theano. CNTK is Microsoft's entry that nobody uses anymore. Theano is still used, but only because it's the grandfather to the whole thing. So, okay. In terms of the dials that you can twiddle on a neural network, the obvious ones from the diagram are the number of hidden layers, how many layers deep you go, the width of each of those hidden layers, and the activation functions, which are basically what triggers neurons to fire. But on top of that, and the more important ones that where people have made great strides in the past 10 years or so come with these training ones, which is basically choosing a better loss function optimizer, initialization, normalization, regularization, and learning rate schedule. We will come on to these in the next 10 minutes or so. This is quite a fun one to play with. I don't know if we have time, but if you want to fiddle with this in the background, if you go to playground.tensorflow.org, you have this rather fun thing. I'll also turn it to light mode so you can see it, where you can say, here's my neural network with 2 inputs, 4 layers and 2 here. I'm going to train it on this data as a classifier to learn that these are orange and these are blue, and you do that, and it does quite a good job of classifying those as being blue. And you can say, what if I added 4 neurons? Does that make any difference? And it's quite good. You can try this problem, and it does that. And it does a pretty good job of doing that. And you can try the super hard problem, which is actually virtually impossible to solve with this, where you're trying to learn this spiral classification here. And here it will struggle quite a lot, but you can see it having go at learning this slowly. We'll add some more layers and make them wider and deeper. So this is a fun thing to play with, and we'll see if that. So you can see here, it's kind of learned something that classifies these outer ones here, but will classify these ones incorrectly. But again, it's sort of learning the outer stuff, and you can see kind of as it trains these. It's quite a fun thing. I would encourage you to have a look at it. There's also a few other things you do. There's also do some fun, funky stuff here as it tries to learn. I would be very impressed if you can get it to learn this with this setup. All right. Okay. So the first thing to talk about when we talk about tuning these various bits and these various dials on the neural network is that this is both the advantage and the main drawback of them. Basically, coming up with new combinations of these is a research field in and of its own self, but because there's so many, it can be quite bewildering. There are some automated tools for doing this, but if I'm being honest, this is very much a big unsolved problem in the field to do this well, and there's a level at which these only resolve some of the major issues in making these things. So with activation functions, there's now quite a zoo of these. These are the things that tell you whether or not to fire. So you have an input that comes in as a real number and an output that tells you whether or not to do that. So the first thing is an activation function that basically just takes in the input and gives the output. That's a non-activation function, which is only included for the purposes of saying that you do want to do that for often an output layer. The original activation function was what neurons actually use, which is just a step function, where you sort of do nothing and then you fire if you are above 0 input. A tanh function is a smooth version of that that moves between -1 and 1, and this, because it's smooth, is quite nice because it means it's differentiable in a way that a step function is not, so it means we can apply these gradient descent algorithms. Logistic is just basically a tanh function, but shifted between 0 and 1 slightly otherwise. ReLU is one of the big guns nowadays, and this is basically, this is differentiable because it's flat here, but you have a 0 gradient. But it's often useful to consider a smooth version of ReLU, like Soft+, or a leaky ReLU, which is not quite 0 at this end, or an LU, which goes exponentially at the bottom to -1, or a CellU, which is a thing, I don't get, which is a Gaussian exponential linear unit. So ReLU stands for rectilinear rectified linear unit. Is that right? Yes. Exponential would be exponential linear unit. Anyone know what SE stands for? I think I've got it later.
Sinusoidal?
Not quite. No, it's something else. G is Gaussian. GALU is probably the most recent of these. There's a whole load of these. In practice, what matters more is understanding when and why you would use them. Smoothness is generally a good shout. Saturation, i.e. whether these things go to 0 or infinity, i.e. whether these things have a hard bound at 0 or go on to infinity. So for example, the ReLU has a hard bound here, so in some sense it saturates at this point, whereas the leaky ReLU has no saturation. It does technically go to -infinity. And smoothness can be quite useful. And also that these take different roles depending on the layer. So in the middle of a network, these can basically change how you train things, and you don't, generally you would just use a leaky ReLU or some of the other defaults. But at the output layer, it can be useful to impose positivity with a softmax function or a ReLU or something like that. Okay. This is a slide that's probably worth keeping, which is just general typical architectures that you might want to try as you sort of play with these things. Your input neurons are defined by how many input features you have. Your output neurons are defined by how many output features you have. And then the hidden layers between 1 and 5 and between 10 and 100 is probably a good word for number of layers and width of layers. And then the hidden activation, ReLU is a good shout, or CellU, or its various variants. We'll come on to other things later. And then the output activation depends on what you're looking for. If you have positive outputs, the ReLU or SOP is a good idea. Bound outputs, a logistic is a good idea. And the loss function, mean squared error, unless you know you've got outliers, then try the mean average error or the Hoover as we discussed. Okay, for the number of hidden layers, it's good to start off with 1 or 2 and gradually increase if you find you need it. And again, using pre-churn network can be good for transfer learning, as we discussed earlier. But again, technically, often a single layer will do. So it's often worth trying to see whether a single layer neural network will do you a good job of a regression or a classification problem before adding extra layers. The width of the hidden layers, historically, people had this idea that you should start off with lots and gradually ramp down as you aim to this. In practice, that makes very little difference with modern training algorithms, and it adds a whole lot of extra tuning parameters. So most people tend to start off with rectangular neural networks by default, i.e. just having the same width that could be between 10 and 100, as I said, rather than having different widths for each layer, unless you're trying to do something specific like autoencoders. And then when we're building these neural networks, in general, you have 3 different ways of building these, and 3 different APIs: a sequential API, a functional API, and a subclass API, which brings me on to the next set of slides. Okay, so we'll have a look at what this actually looks like in practice. Okay, so we're now at example 3, which is neural network training. So here's Keras, and we're going to do PyTorch later. So you say from TensorFlow import Keras, and you start by defining a model with this thing here, and this is a sequential model for this. And all we do here is we add the layers where we have the input here. Remember, X was our input data, and this here would be about 9, I think, for our original problem. And then we add sort of layer on top of that. So you can delete lines here, and that will do be a 2-layer neural network. Otherwise, and just having a ReLU is probably a good idea to start off with. That is fine. And then this thing here is quite a useful tool to look at, which basically gives you a summary of the model. So you can see we have a sequential model that has 30 in 3 layers, and in total there are 2,191 trainable parameters in this model, which is quite a lot. Particularly given that there's only over 15,000 data points. And this is one of the things that is one of these, again, hidden secrets of this. Often for the really deep networks, you often have many, many more trainable parameters than data points that you're training on, yet it still works. And it means that a lot of the intuition that one has around getting stuck in local minima is not really there, because if you've got 1,000, if you've got more trainable parameters than data points, in reality, you are intersecting with some hypersurface in that plane. So it's quite a subtle one. Here, this is fine because we have enough to go on, and this is where regularization becomes important, basically. So here, you then sort of define the model with this compile step that defines the loss function, the optimizer, and the metrics. Remember, there was this thing where we defined the anatomy of the network, which is this bit here, and here we defined the training procedure. Again, we're going to say mean squared error, which is the first thing you think of, the stochastic gradient descent, which is a relatively straightforward one, and then we're going to also record an accuracy, and we do the same thing here where we take the train test split, only this time instead of splitting the total data, we're taking the training data and splitting it into training data and validation data. So when we do that, we get this, and this is generally what it looks like in TensorFlow, where you can see this kind of epoch 5, 6, 7, all the way up to that, and it takes a bit of time. In terms of looking at this, you can see it starts out with a loss of 3, then move to a loss of 1.8, and it's generally coming down. And the accuracy for this problem is not great, but you will find that this in general gives you an answer that is pretty good. Certainly as good as all the previous things that we tried earlier, and at least it's a neural network way of doing it. So we'll let that train for a bit. The laptop is struggling. training. Discuss a few other things. So the next thing after this, whilst this is training, is that in addition to the sequential API, you can have the functional API. And this thing here trains what's called a wide and deep network, which is where you have your input parameters, and you have two deep layers, and the output parameters. And you sort of have these being connected as before to the output. And then you have a deep portion and a shallow portion, which basically just connects this directly to that. And then this concatenates these two to give an output. So this is a wide and a deep network in that you simultaneously train both a deep network and one that's basically a line that connects directly to this layer. And in principle, that gives the model the flexibility to do both shallow and deep learning at the same time and learn features separately. This is not something that the details of this are less important than the fact that this is not something that you would be able to construct with a sequential API, because you have complicated graphical relationships between these things. You also might find that you might want to split the inputs and have only some of the inputs going into this and only some of the inputs going into that. And again, the functional API is a way to do that. And the principle here is that you take, instead of just defining an array of these things, you define the functional graphical relationship between them by saying, I've got an input layer, which is a Keras layer of this, and a dense layer, which is defined with this bit here, that takes the input as its input, which is what this extra pair of graphics does. The hidden 2 layer takes hidden 1 as an input, and the concatenation layer takes both the input and the hidden ones as its input. So this here is describing this structure here, where you've got inputs, 2 dense, and a concatenation layer. So you've got input, 2 hidden layers, and a concatenation layer, and the output being sort of just, again, yeah, the soft plus of that, basically. And then that gives you the model, which we can in principle fit. This should now have finished training by now. So once the original model, we have that. You see this is what our training curves looks like. The blue one coming down, and the green one coming down, and you can see it's starting to, whilst the blue one continues to get better and better, the green one has leveled off by this point. So ideally we would have sort of a nice sort of upward peak, but in practice it never looks quite that nice. But in terms of making predictions, this doesn't do a terrible job. Orange is the prediction of the neural network. Blue is the linear regressor, so it does a slightly better job, but predictions is slightly tighter. But again, it is hard to predict the weather in Britain. And we can train those two here. And the only other kind of, the third type of API is the TensorFlow subclassing API, which basically works by, the subclassing API uses Pythonic duck typing to say whatever you like. It's therefore, which allows you to create dynamic models where you might want to break these connections as you go, or depending on the input. So you might want to say, if the input is above a certain threshold, add an extra layer. Or if the input is above something else, that becomes much harder to code. Pythonically, it's very straightforward, but it's generally much less efficient to do it that way because you don't know the structure of the network anymore. So we'll finish that there. PyTorch, on the other hand, looks like this. So here, this is the PyTorch equivalent of doing the same sequential model, which is where we define, instead of a set of layers that were relatively straightforward, you define, it's a bit more separated. So you have a linear input followed by a ReLU, a linear layer followed by a ReLU, a linear layer followed by a subclass. This is the same thing as before, only back in the TensorFlow, this was in one line, where you would say it's a dense layer with a ReLU activation. In PyTorch, that is separated, and therefore by being separated is more flexible because you can add several different things before you put in the activation layer, before you put in the linear layer. So it separates these two out. You then define a loss function, an optimizer, by using torch.nn MSE loss, optimizer here, and then you can train these things. So this stuff is all fine, in that you define your sequential model, your loss function, your optimizer as nice Pythonic objects. So there's nothing too nasty about that. This here is the PyTorch gubbins, where basically you need to convert between numpy values and what Torch considers a tensor. And again, warning, whenever you read about PyTorch, they generally have all the documentation with leagues and leagues of tensor stuff that is actually nowhere near as important as they think it is. So people will go on and on about sort of all these tensor objects because that's what people think about when they're researching it, and it matters, but it's not a good start point for people. So this here compresses all of that stuff about tensor variables and things like that into that line, and then we forget about it. It looks very similar to the rest of the code people do here. So as a warning, when you read about PyTorch, you can skip a lot of that tensor stuff, just knowing that it's all about this, like the backpropagation and automatic gradients. It's just a way of sort of thinking about data that matters later on, but not at the start. And then this here is the meat of the code. Notice again, in the same way that here, where things are much more separated, things here are much more separated. The user needs to define a lot more in PyTorch in comparison with Keras. With Keras, there's just one function you say, and you call it train, so it's a good thing to get started with. Whereas here, it forces you to be a bit more circumspect about how much you want to do it. Here, all we do here is we say for 50 boxes we had before, I'm going to compute a training loss to report, and I make a prediction, I compute the loss function, I then differentiate it, I make a step here, and then zero the gradients for the next step. It is useful for researchers to be able to separate those two in a way that Keras insulates you from. So and this is one of these critical differences between it. PyTorch gives you a Pythonic way of doing this kind of research. TensorFlow gives you a full-on symbolic computation library of doing this. Keras makes it harder to do this kind of work. So PyTorch is good for this kind of thing. We do the same thing with the validation data, and we do this, and hopefully, I'll need to find that up there. Sorry, to execute that cell, and then we train. Oh, hang on, so it doesn't involve there, as I was gesturing. Okay. You will note that this is faster than Keras as well, and that it gets the answer quicker because of all that tensor governance. Whereas sort of Keras is kind of CPU, sort of only really CPU ready. There's a lot of stuff under the hood that goes on in this step here, which is why they spend so much time talking about it. But the end result for most people is that you have to do a bit of coaxing the data into the correct tensor floating point format before you can get started. But once you've done that, it's then much faster, and you never really think about it again. And we plot predictors again, and again it looks pretty good as a rough kind of idea of kind of predicting the sunshine from comparing the actual sunshine to what it really did. Okay, I would encourage you after the fact to have a look at these things here and have a play with these. In particular, you can get a lot out of this just by sort of adding in extra layers and seeing what happens, or changing these activation functions. And this gives you sort of a comparison between the two, and I've used some of that. I'm going to finish with a few more things about some of the more modern neural network trainings. So the big problem with training deep networks is exploding or vanishing gradients. So a vanishing gradient is relatively straightforward. We kind of saw it as why it's a problem because it creates plateaus. But the reason why it can happen is that if you have saturating activation functions, you find that if you have your inputs sort of oversaturating all the time, you end up sort of getting stuck in these plateaus of, say, a tangent function or otherwise. And if you have too much of the network with those active, it's unable to get off those plateaus. Exploding gradients are a bit less regular in the kind of things we're considering here, but if we look at recurrent neural networks, again, that happens where gradients are allowed to grow without bound. So again, just thinking back to that diagram of getting stuck in local minimum or getting stuck in plateaus, really fixing this, all it comes down to is adjusting how you initialize the weights. And it took us an embarrassingly long time to realize that this was a big problem, when actually, when you explain it carefully, it's a relatively straightforward and obvious when you think of it. But if you initialize the weights randomly, as you expect, with Gaussians with mean 0 and variance 1, and you put those into an activation function, those in general won't come out with mean 0 and variance 1. They'll come out with a shifted mean and a variance that's a bit more squished. So all you do to start in a better place in this space is to just make sure that the initialization spread agrees with the symmetries of the activation functions that you're considering. And you then borrow these terminology called fan in and fan out. That should be an out there rather than in. Where basically fan in is the number of the number of connections going into a node, and fan out is the number of connections coming out of a node. And if you just take the average of those, that is what you should use to tune how spread your initial randomly distributed weights are. And when you do that, you get enormous improvements in performance, because previously you were just getting stuck on plateaus, whereas if you're just a bit more careful about making sure that you start in a place where they can all easily adjust themselves and the gradient is not on a plateau, you get a lot of very, very good performance. And you get these three different forms of initialization, which are named after who discovered them: Glorat, he, and Lacan. And basically, all it amounts to is you need to pair your initialization with the correct activation function. So, and this is something you would look up if you want to do it, and a lot of the things now implemented by default. But this was a big upgrade. Another way to deal with the vanishing gradients problem is to choose a non-saturating activation function, i.e. something that goes sort of like a ReLU, which doesn't saturate forwards, and a leaky ReLU, which doesn't saturate backwards. This is again something where this is not how Mother Nature does it, and therefore this was something where we sort of undid some of that assumption about should we be mirroring how biological neural networks work, sort of dramatically improve things. You need to be a bit careful because the leaky ReLU has this extra parameter alpha, which is how leaky it is, and you can view that as another high parameter twiddle. You can either set it to be a large leak or a small leak. You can randomize it, or you can even fit it along with the other parameters. There was some very impressive stuff by Google where they did this in a full fit, and you got some incredible performance, although again a little prone to overfitting. S stands for self-normalizing rather than another end. So,
I couldn't tell the colours apart on the graph once you had them, but there was one that was nice.
So yeah, and there's a few other these linear units that people tend to work with, where the LU is another choice, and the GELU is some people call it Gaussian, and some people call it the Google exponential linear unit. So there's a lot of different things that people work on there. But again, that's sort of the take-home message here is that thinking about it in terms of a research problem of where you're trying to work out what a human brain does is not necessarily the correct way to do things. Batch normalization is another thing that's very much the state of the art. And the idea here is that the same normalization procedure that you would do manually at the front end by normalizing things to have mean, zero, variance 1, you can actually get the neural network to do in between layers. Again, you can imagine with PyTorch, with its split layers, it's the kind of thing that's easier to implement in that. You need to therefore, and it's called batch normalization because obviously you can only normalize with respect to the data that you've seen, and you need to be careful that you then don't use the training data to do that, so you have to sort of record an average one to use eventually. But this self-normalizing thing is also great because in principle it starts to remove some of the need for standardization that other people, that is at the moment in the regime of what humans do. It can be quite a lot slower than the other case, so this is something that people like using, but it's not that. It's got a few things associated with it. So batch normalization is something you can turn on, but just be aware it can slow things down. And then the other big thing here is faster optimizers. So most of you have probably heard of this bottom one, Adam optimizer, because it's the default one that people tend to choose. It's built out of a whole load of other things. So the first change you make to the default sort of learning rate of gradient descent is give it some momentum, which is that you have an extra variable that, like a bowling ball rolling down a hill, means that it's got some memory of where it was traveling before. The maths is relatively straightforward, and you can view this as being a poor man's Hamiltonian Monte Carlo. It's a very sort of a way of giving it a bit of extra sort of memory in its trajectory, so it's not bouncing around all over the place. Nesterov accelerated gradients basically make a change where you use gradients slightly ahead of the path rather than where you currently are, and that can make quite informed decisions about the correct way to turn. Adagrad again is one of these things where we were talking about the importance of non-covariance. Basically, what that does is it records the gradients and measures their average squared size to give you something that's like a covariance matrix, or sort of give you some quantification of this ellipticity that you then use to, instead of taking the normal gradient descent, allow you to basically scale your directions in the directions of greatest change this way. And RMS prop changes Adagrad by making that averaging process an exponential moving average rather than just a permanent memory moving average. And ADAM, which is adaptive moment estimation, basically combines all of those by combining both RMS prop and momentum Nesterov stuff. And NADAM is that with Nesterov. So ADAM, which is this one that's now a default, has a lot of extra stuff gone into it that people have tried. For all that, and for all that it is a popular default, it's always worth trying that just your default stochastic gradient descent doesn't also have good performance, because this does add a lot of structure onto this that is not always wise for a lot of things that you might work on. And there's another sort of extra tuning parameter of learning rate scheduling that's really a dark art for only those people that sort of are really keen. But basically, this is where you can adjust how fast you learn. It's similar to simulated reading. And then finally, in the final minute or so, regularization, we've already mentioned L1 and L2, but the two big names here that hit the field in 2016 and are still having a lot of press, and in particular, it's quite nice because this is very much a Cambridge-based sort of work by Zubin and Yaron, where basically instead of having these functional regularizations, you have this dropout regularization, which is where you turn off nodes randomly during training, stochastically, and you find that doing that greatly improves generalizability because the neural network can never be dependent on only one node, basically. So the idea being that by having this randomness of whether you turn things on and off can be extremely effective. And then Zubin and Yaron made their names in this field by saying, hang on, if we also do that at testing time, but we do it with an Markov chain Monte Carlo framework where you basically test that, you can get an error bar and an interpretation in terms of approximate Bayesian computation. So this is a very big paper in the field from some very local people. Okay, and I will finish on those guidelines here, which come from Kirill, but basically I would sort of say this is a good thing to start off with, and I don't want to take up any more time. If you take nothing else away, these three books are ones I'd recommend, particularly the first two. I hope I gave you something of a flavour of the difference between Keras and PyTorch and TensorFlow, and something of the complexity of anatomy training. And if you use these as notes for playing with the notebooks that we have that I've provided, these give you a reasonable way to think around the field of deep learning. And I'll finish there. All right.
Time for a quick question or two.
What can you use if you're in a situation in which you have few data, because data is costly, but you can pick where you search for your data?
So what machine learning algorithm is good for doing that? So the state of the art there would be a Bayesian optimization approach for picking new data points, where you have a small amount of data and you want to determine where to pick new data from. It depends on how broadly you interpret the thing data. Is data sort of like real world data from people, or is it sort of more in the realm of generating new simulations?
The latter.
Bayesian optimization. with Bayesian Gaussian processes. But that's the short answer.
So you mentioned the choices you might make in how you design the network, such as that diagram behind you. And is there anything other than just intuition that guides you when you're looking at your data sets and your feature set as to how you're going to design the network?
The short answer is intuition and experience, and people make careers in this. It's a whole field in itself, but the problem of how you could automate this is a big research problem. I work on this in the context of Bayesian neural networks, where you try and use the Bayesian evidence or the marginal likelihood as a probability over networks, but we're a long way from solving it. It's, the short answer is this is a whole art in and of itself, and we all want it to be better than this.